Last week we did the hard work of setting up the theory of the Lebesgue integral. This week we reap the rewards. We shall prove various convergence theorems that make the Lebesgue integral far more suited for analysis compared to the Riemann integral. The first theorem that we are going to establish is the Levi's monotone convergence theorem. Recall that we had first defined the integral for step functions. Then we considered increasing sequences of step functions that converge to a function such that the integrals are bounded, and the limits of such functions we called upper functions, and then we defined the integral for upper functions. Now what we are going to show is the moment that the integrals of step functions are bounded, then automatically the step functions converge and the resultant function is an upper function. So essentially we are trying to see that the process by which we created the Lebesgue integral sort of is closed. In some sense we are trying to prove a completeness result. Without further ado, we are going to first prove Levi's monotone convergence theorem for step functions. Then we will prove the same theorem for upper functions, and finally we will deal with the general class of Lebesgue integrable functions. We are essentially going to show that this class is closed under increasing functions. So you will understand better once I state the theorem. So the setup is as follows. Let Sn from I to R be an increasing sequence of step functions. Assume that integral over I Sn is bounded. Then the conclusion is then Sn increases almost everywhere to a function f, which is in the class of upper functions. It's an upper integrable function, and the integral of this function f is nothing but limit n going to infinity of integral over I Sn. Okay, so notice that the crucial thing that is present in this theorem is that we automatically get a function f for free. When we defined this class of upper functions, we say that Sn generates f if these Sn's are increasing, as well as Sn increasing to f almost everywhere. Then and we also assume that this integral of Isn is also bounded. Under those circumstances we say that f is an upper function. Here we get that upper function for free just from the fact that the integrals are bounded. So you can already see that this is stating quite a non-trivial thing. Let's go on to the proof. First, what we are going to do is we are going to consider the case only of non-negative functions. What you do is consider Sn minus S1. Okay. Now notice that if this sequence, this sequence satisfies all the hypotheses of the theorem and is also non-negative, which is going to prove very useful. Okay, if we could show the conclusion of the theorem, if we could show that the theorem holds for Sn minus S1, then it automatically holds for Sn as well. Well, if Sn minus S1 increases almost everywhere to a function g, then the required function f is nothing but g plus s1, as you can see. So we will prove it. We will henceforth, so without loss of generality, we will assume each Sn is itself greater than or equal to 0. Just for ease of notation, I don't want to introduce another sequence of step functions because I'm going to do that now for the purposes of the proof anyway. So not to deal with 3 different sequences of step functions, to keep the notation sane, I'm going to just call it Sn again. We are going to assume Sn's are non-negative. Okay, now Sn's are increasing everywhere. In fact, that's our assumption. How can Sn fail to converge at a point? Well, the only way by which an increasing sequence can fail to converge at a point is if it diverges to plus infinity. Now what we are going to do is, we are going to control the behavior of Sn by constructing an auxiliary sequence of step functions that are special in the sense that they are integer valued step functions. So how are we going to do this? Well, let m greater than 0 be an upper bound for integral over I Sn, this collection. We know that the limit exists. We know that this is an increasing sequence. So let m be an upper bound for it. Okay. Now fix epsilon greater than 0. Let d denote the set of points of I, on which Sn diverges. Now goal to show that D can be covered by a countable union of intervals whose net length is less than epsilon. That's the goal. Since epsilon was arbitrary, that would show that the set of points where Sn diverges is actually a set of measures 0, which will in fact show that Sn increases almost everywhere to some function f. Okay, now I said we are going to construct a sequence of auxiliary step functions which will sort of be integer valued. So what we do is, we defined Tn to be epsilon by 2m times Sn integer part. Integer part just means it will remove the decimal part and leave you with the integer. This is also known as the, I think it's called the floor function or something. It is the greatest integer that is less than or equal to that particular number. Okay. So what we are doing is, we are going to take the integer part of this. Now, when dividing by 2m, what we achieve is the integral of Tn is going to be quite small, simply because we have already divided by the integral value, and we have made it even smaller by multiplying by epsilon. Okay, now observe that just by definition this is less than or equal to epsilon by 2m Sn. That's why what I said just makes sense. So the integral of this Tn is going to be quite small. It's going to be less than epsilon by 2 in fact. And notice that if Sn of x is convergent, then Sn of x is bounded above because it's an increasing sequence. Then Tn of x is bounded above and therefore convergent. In fact, because Tn is integer valued, the only way by which Tn could converge is after a point it becomes constant. So this is just a concrete version of the abstract fact that any convergence sequence in a discrete metric space must be eventually constant. This is a concrete realization of a fact you're familiar with from several weeks ago. Okay, so Tnx being integer valued will have to be eventually constant provided Snx converges. On the other hand, if Snx diverges, then so does Tnx. That's straightforward to see just by the way Tn has been defined. If Snx diverges, then so does Tn. Well, Tn is integer valued. How can in fact positive integer, non-negative integer valued, how can a non-negative integer valued sequence diverge? Well, only way by which it can diverge is it increases its value by +1 infinitely often. So motivated by what I just said, we define the set Dn by definition to be the set of all x in I such that Tn plus 1x is minus Tnx is greater than or equal to 1. Okay, so Dn consists of those points x in the interval I where the function Tn plus 1 exceeds Tnx by at least 1. So there is a jump. Okay, there is a jump. Now the set of points where Tn diverges is precisely the set of points x which on which this sequence Tn jumps infinitely often. Those are the points at which the sequence Tn will diverge. Okay, so we can express D as a subset of union n equal to 1 to infinity Dn. Notice that the right hand side set is far larger than what we actually want. Even though this set is really large, the proof will still work. Why is this set really large? Well, it looks at all those points where the sequence of functions Tn jumps at least once, whereas we want to isolate those points where there is infinitely many jumps. So this is sort of like a very bad estimate, but surprisingly even this very bad estimate works. Okay, now remember the goal was to show that D can be covered by a countable union of intervals whose net length is less than epsilon. Well, turns out that the net length of this Dn n equals 1 to infinity is itself less than epsilon. Okay, also because Tn's are step functions and Dn's measure the places where there is a jump, it's clear that each Dn is a finite union of intervals. Okay, simply because Tn plus 1 and Tn are both step functions and we are simply measuring those points. We are simply putting together in a set those points where Tn plus 1 jumps ahead of Tn. What you do is you look at a partition, common refinement of the partition with respect to which Tn plus 1 and Tn are step functions. You look at a common refinement and you will notice that the jumps will always have to occur on a finite union of intervals. Okay, now how do we find out the length of Dn? Well, observe that integral over I Tn plus 1 minus Tn. Well, what will this measure? This will be non-zero precisely at those places where there is a jump. Okay, and because the set Dn is a subset of I, we first have this obvious and trivial estimate. Note here I'm using the fact that these functions are Tn plus 1 minus Tn is a non-negative, and this is of course greater than or equal to integral over Dn 1, right? Because on Dn, Tn plus 1 minus Tn is at least 1, and this is just length of Dn. Oh. Okay, so note that maybe I did not introduce this notation. This is just the length of Dn. Since Dn is a finite unit of intervals, you can find out the length by just summing up the lengths of the intervals. Okay, excellent. Now our goal is to estimate the length of the union of Dn's. Well, of course, you can do that by saying union of Dn n equal to 1 to infinity. The length of this is certainly less than or equal to limit m going to infinity summation n equals 1 to m of mod Dn. Okay, and from what we have established, this is less than or equal to limit m going to infinity of sum n equal to 1 to m integral over I Tn plus 1 minus Tn. By exactly the previous line. By this line, we immediately get this. But this is sort of like a cascading sum. This is equal to limit m going to infinity integral over I Tn plus 1 minus Tn, or rather Tm plus 1, sorry. This is Tm plus 1 minus T1. Okay, and since Tm plus 1 minus T1 and this T1 is a non-negative function, we can just get rid of this in an estimate and write that this is less than or equal to limit m going to infinity integral over I of Tm, which is going to be less than or equal to epsilon by 2. Why is this going to be less? Let's elaborate that. Well, this is less than or equal to integral over I epsilon by 2m Sm, which is going to be less than or equal to epsilon by 2. Okay, so this shows that the length summation n equals 1 to infinity of mod Dn is less than epsilon as claimed. So conclusion is Sn increases almost everywhere to a function f. Okay, of course this function f is not defined everywhere, so where we set f of x to be 0 if Snx diverges. We don't get a function f just from the convergence, because at those points where Snx diverges, we don't know what the value of f of x is, so we just set it to be 0 there. Rest of the points we just take the limit of Snx. Okay, then by definition f is an upper function and Sn generates f, and therefore integral over if is actually just by definition limit n going to infinity integral over I Sn. So this concludes the proof of Levi's theorem, Levi's monotone convergence theorem for step functions. In the next video, we will extend this to upper functions, and in the video after that, we will extend it to the Lebesgue integrable functions. This is a course on real analysis, and you have just watched the video on the Levi monotone convergence theorem for step functions.